Video, what we're going to look at is how energy is talked about or discussed in chemical reactions. But before we can do that, let's look at what energy actually happens to be. Energy is defined as the capacity to supply heat or do work. And in two general classifications, energy can be referred to as potential energy or kinetic energy. And so potential energy is essentially stored energy, and kinetic energy is the energy of motion. And these are very nice definitions that make a lot of sense when we talk about physics, but how does that relate to chemistry? So the study of energy in chemistry is really called thermochemistry. And what we're really referring to in energy is in the form of what we call thermal energy. And thermal energy, another way to refer to that is just heat energy. And so there are really two ways thermal or heat energy can be discussed when it comes to a chemical reaction. Either that energy, heat energy or thermal energy, is absorbed in a chemical reaction, or it is released. And there are terms that we use to describe a chemical reaction that absorbs or releases energy. When you absorb, you're called an endothermic reaction. And when you release energy, you're called an exothermic reaction. And so how a chemical reaction might look when we're talking about thermochemistry, or how much heat is either absorbed or released in a chemical reaction, could be shown in this chemical reaction here, where you have methane, CH4, that reacts with 2 molecules of oxygen to produce 1 molecule of CO2 and 2 molecules of water. And the idea here is that how thermochemistry, or the two types, kinetic and potential energy, are related to a chemical reaction. We tend to think of bonds as potential energy. And so you could actually calculate how much potential energy is stored in all of the bonds in a substance by actually measuring how much energy is in each one of those types of bonds, including double bonds like you see between 2 oxygen atoms and on an O2 molecule. And how that converts from potential to kinetic are these bonds are broken, and when they are broken, they're rearranged, the atoms are rearranged to form new bonds that you see over here in red. And when these new bonds form, that moves back from kinetic energy to potential energy. And it turns out that the difference in bond energy, stored or potential bond energy, between reactants versus products can tell us whether or not energy was absorbed or released in that chemical reaction. And when this particular kind of chemical reaction occurs, methane reacting in oxygen to produce CO2 and water, it turns out that there's actually a lot of heat that is given off with that. So that means some of the potential energy that converted to kinetic energy, the kinetic energy is lost in the form of thermal energy or heat. And we can actually measure that value. How do we do that? Well, it turns out that we have to have some way of measuring energy. In chemistry, we tend to use a couple of different types of units. A couple of those might be the term called calories and a joule. And a calorie is defined as the amount of energy that it takes for you to, required to increase a substance with this substance being specifically water by 1 degree Celsius in 1 gram of that substance. So in our case, water. The second unit is called a joule, and this is defined as the amount of energy required to force or rather when a force of 1 Newton moves an object 1 meter. So you could write a joule as equivalent to 1 kilogram meters squared per second squared, which would be essentially a Newton times a meter. You most likely won't need this particular unit or conversion factor in this chapter, but you will later on towards the end of the semester. But if I could relate a joule to a calorie, it turns out that 1 calorie is equal to 4.184 joules. And this actually might be a useful conversion factor for you later on. So let's see how they are used in in equations. And so these are really useful values that you can measure. One of them is called the heat capacity. And heat capacity is something that is an extensive property. It takes into account the mass of the substance and the substance itself, and looks at changes in temperature, and you're able to actually calculate a value about that substance. Another way to think about calculations of thermochemistry would be this term called specific heat capacity. And the specific heat capacity takes into account just the substance. It doesn't actually take into account the mass of the substance that you have for this value, and it's considered an intensive property. I want you to note and look at the way that I wrote these two equations, that the capital C is what we call the heat capacity. The Q is the amount of heat, energy in the system, and the delta T is actually the temperature of the final minus the temperature initial of the change in temperature. But notice how in the specific heat capacity I still use the letter C. Note that this is a small letter C. So the heat capacity has a large one, specific heat capacity has a small one. Sometimes I have seen, instead of using a letter C for the specific heat capacity, some people use the letter S so that you can distinguish capital letter and lowercase letters between the two equations. Your text continuously uses C, so we'll use C from now on. So what we're going to do is we're going to use these two equations in order for us to find ultimately values about a substance in the form of thermochemistry. Keep in mind that Q over here in the specific heat capacity is still heat energy. Delta T here is still T final minus T initial. The M over here is new compared to the heat capacity equation, and that's just the mass in grams of the substance. So let's try a practice problem using those equations. So this problem says how much heat in joules must be added to a 5.00 times 10 to the 2 gram iron skillet to increase its temperature from 25 degrees C to 250 degrees C. Keeping in mind that the specific heat of iron is 0.451 joules per gram degree C. So in this particular question, we're going to solve the equation of the specific heat capacity for how much heat. So we're going to solve for Q. That's what we're looking for here. So Q will equal all of the other variables on the other side, the right-hand side. And typically this is written in the form of mass times specific heat times delta T. So we'll read that as Q equals MC delta T. And so do we have M? We're going to write all of our information over here on the right-hand side. Yes, 5.00 times 10 to the 2 grams. Do we have C? Yes, 0.451 joules per gram degree C. And do we have delta T? Well, we have T final minus T and T initial, so we have to solve for delta T. So our final value is 250 degrees C, and then our initial was 25 degrees C. So our delta T is actually 225 degrees C. So we do have all of the values that are needed to solve for Q. So we just plug everything in. 225 degrees C times 0.451 joules per gram degree C times the delta T, which is 225 degrees C. And this gives us a value that equals, on my calculator, I get a value, but I think I wrote mass wrong here. Let me do that correctly. It is 5.00 times 10 to the 2 grams. So what will happen here is the grams will cancel, degrees C will cancel, and then you're left in joules, which is what we want in energy value. So when we put this into our calculator, you get this long number. We want to, I get something like this, 50,737.5. And so I need to take into account sig fig. So I have 3 here, 3 here, 3 here. So as far as I can go is to the 7. I'm going to use the previous number to round up or down, and it's going to just stay as is. So this gives me 50,700 joules. I will say sometimes that is written in kilojoules, so you'll see that a lot when it comes to energy. And so you just move that decimal over 3 times to the left, and that would be 50.7 kilojoules. Either answer is perfectly fine, either in joules or kilojoules. All right, let's try another problem. It says a piece of unknown metal weighs 217 grams. When the piece of metal absorbs 1.43 kilojoules of heat, its temperature increases from 24.5 degrees C to 39.1 degrees C. Determine the specific heat of this metal and predict its identity. And I'll show you how to do the predicting identity in here in a second. So we're going to still use the same equation, Q equals MC delta T. And I actually wrote that. We're wanting to determine the specific heat, so we can rearrange that back to C equals Q over M delta T. Okay, so Q actually is our value here of 1.43, but it's kilojoules. We need to make sure that it's in joules in the problem, and so that's actually 1, 2, 3. Move the decimal 3 times to the right. 1,430 joules. M, do we have M? Yes, we have 217 grams. And do we have delta T? When we have our changes or our 2 temperatures, we can figure it out. So T final minus T initial. Our T final is 39.1, and we're going to subtract 24.5. That's going to give us a value of 14.6 degrees C. So now we can just plug everything in. So 1430 joules, our mass 217 grams, temperature delta T is 14.6 degrees C, and then our specific heat should end up being a value of 0.451, rounded to the third significant figure, joules per gram degrees C, because none of these units cancel. So they all belong in the unit. And so what you do so we figured out the specific heat of the metal. We've got that answer. But we need to predict its identity. So what kind of metal? Turns out that the specific heat capacity is specific to a substance. And so you can look up the specific heat capacities of known substances in a table, or if you're just so willing to Google, you're welcome to do that. There is a table in your textbook. That's table 5.1. And it turns out that there's just a small subset of specific heat capacities. Highlight that. That you can use to figure out what that is. And so you just look for our answer of 0.451 joules per gram degree C and see if there's one that's close to that. And it looks like this one's actually the closest one right here. And so we could predict, and we don't know 100% sure, but we could predict that that substance is probably iron, or Fe. Okay, so that's how you do that problem. And so we're going to stop there. These are just a really simple problems for using one particular equation, and that's that equation, the specific heat capacity equation. Look for some more energy videos, and I will see you next week.